Alright, it's been a while, like that Stain song, but I'm back and we're going to do more problems. So here's one that we're going to do, and we got to prove a bunch of things. So first, to prove, because we want to prove it's a norm, so to prove the triangle inequality, let mu and nu the elements be complex measures on X. Then, see here, what is the norm of mu plus nu? This is by definition, right, this is mu plus nu, because the norm is defined as the measure of the space. And what is this norm? Well, we could use a number of different definitions here for what the total variation of complex measure is. This one will be most useful, and it's the most intuitive in some sense, and it's also the one that's most easily generalizable. I seem to recall that if you want to talk about measures on arbitrary spaces, or like on more abstract spaces, even you can get to measures that are defined on Banach spaces. So measures taking values in Banach spaces. There's a textbook called Vector Measures. But anyways, I'm pretty sure this is the more abstract definition. So it's just the supremum of the absolute value of the measure applied to each set, the supremum taken over finite partitions of the initial set. And so we've got this, and then we just use the triangle inequality on the absolute value. And I'm just going to put a dot here because, I mean, basically this dot here means replace this with like x equals the disjoint union from 1 to n of e sub j. Oh, and of course these e sub j's obviously belong to m, script m, otherwise this wouldn't make sense. So then what can we do here? This is less than or equal to, well, this supremum is taken over all sums of this form. So you've got this part and this part here are fixed. And you could improve the supremum by taking the supremum separately. Like maybe the sum from 1 to n of mu of... Maybe you can find a different partition that will attain different supremums for each set separately. So basically what we end up with is mu ej, and then we add on the supremum. Maybe I should have done the plus at the other end, like on the, like over here, whatever. I know in Russian textbooks it seems to be common to put, like if you had a plus here on a line continuation, to put it on both. And that's actually kind of useful, just so that it's always there and there's no, like, you don't need to look back and forth to see what's going on. But I don't think it's very common in textbooks. But anyways, what is this? This is just by definition mu of x plus nu of x. And that by definition is just mu plus nu. And so the triangle inequality holds. Next, if lambda is some, let's see, this is a complex measure, so this needs to be a complex scalar, then what do? We've got this, the norm of this measure is just by definition the supremum, 1 to n of, we've got this lambda in here, that guy's hanging out, but we can pull him out front, just because this absolute value of lambda just factors out before the sum, and then you can take it outside the supremum as well. And mu ej. And what is that? That's lambda times mu. So there we go. Lastly, if the norm of mu equals 0, just to make it a norm and not a semi-norm, we need to make sure that the absolute value of mu is 0 precisely when mu is the 0 measure. So if this holds, then for all E and M, mu of E plus, then I'll keep doing this neat little thing where you put the plus on both sides. So this is less than or equal to norm of mu, which is equal to 0, because norm of mu of E plus norm of mu of E complement, that's just a particular element of this type of collection. You take that we're taking the supremum over. So certainly if we choose a particular partition of X, a pretty dull one, this isn't going to necessarily get you very close at all to the absolute value of the norm, but we know it must be less than or equal to it because it's a particular element of the thing you're taking supremums over. So yeah, so this is true, and so the absolute value of mu of E is equal to 0, which means that mu of E is equal to 0. So for all sets E in our sigma algebra, the measure of the set is 0. So mu is the 0 measure. Hence, this absolute value thing that we define is indeed a norm on Mx. Alright, well, looks like I'm going to need to use need to scroll down here at some point, but anyways, we'll keep going here. So now for completeness, we will show that every absolutely convergent series, every absolutely convergent series in Mx converges. When I say converges, I mean converges in Mx with respect to this norm that we have on Mx. And this is equivalent to every absolutely convergent series in Mx converging is equivalent to completeness by theorem 5.1. Although, yeah, you might as well have said, like, instead of theorem 5.1, like, when he says, oh, just use theorem 5.1, you have to flip back and you have to look, oh, what is that thing that he proved? But it's just use that absolutely convergent series converge. So anyways, so let UN be a subset of this. So this is a sequence. So this is some sequence in Mx such that the sum converges absolutely. So the sum from 1 to infinity of the absolute values, or the norms, is finite. So now let mu equals the sum from 1 to n of just mu n. I claim mu is a complex measure. Because certainly if the series converges, it's going to converge. Well, if the series converges, it's going to be, if we write it like this, then in order for it to converge in MX, we just need to prove that this series itself satisfies the condition of being in MX. So, scroll down a bit. And let's prove that this is complex measure. First, okay, well, what's a measure? The measure of the empty set has to be 0. So, but this by definition is just the sum of the mu n's, and these we know are complex measures, and so this is 0. Next, what do we want to do now? Okay, I don't care about my updates. I don't want to install your stuff. What are we doing now? We want to prove that this maps into C. So next, in particular, we know that it's going to, it's a sum of complex numbers. And so we know that if this sum, so long as this sum behaves nicely, it's going to be a complex number. But what we need to make sure doesn't happen is that, like, say this goes off to infinity. So we deal with that now. So if E is an element in script M, then we need to bound the mu measure of E. So this by definition is 1 to infinity mu n of E. And this is less than or equal to the sum from 1 to infinity of mu n E. Just bringing the absolute values inside. And this is less than or equal to the sum from 1 to infinity. Certainly this is less than or equal to the measure of the whole space in absolute value. And we know by assumption that this is finite. So mu maps into C. And in particular, mu of x, the absolute value of the mu of x is finite. Next, we gotta prove that if you have a disjoint, if you have a countable collection of disjoint sets, then the measure of the union is equal to the sum of the measures. So, what you basically want to do here is, because mu is defined as a sum, we're going to have two sums, and we're going to want to be able to flip them. So, what do you do when you want to flip sums? Well, what is a sum? A sum is basically integration with respect to the counting measure. So we're going to use Fubini's theorem here. So next, if we have a disjoint collection in N, well, yeah, we'll call this, well, the elements are in script M, and they're disjoint in X. Then what do we know? Just in order to apply Fubini's theorem, we need to make sure that these things don't, like, blow up. So the measure of the union of the EIs is finite. And so basically what that means is that, let's see here. So anyways, thus, and this next thing is important. Since N is sigma finite, with respect to the counting measure. And that's something that is very easy to forget in Fubini's theorem. It's one of those technical things, like you learn these theorems and you learn, like, there's the main meat of the theorem. Like, the meat of Fubini's theorem is that you flip the order of the integrals. But there's those technicalities that you need to keep in mind as well. And this one's important because counting measures you have to be really careful with. Because if you have a counting measure on a uncountable space, then that's a recipe for very strange behavior to happen. And so it's really important to specifically point out that we're satisfying the sigma finiteness condition when we're using Fubini's theorem. Then by Fubini, here, we have measure of the union from 1 to infinity of EI is the sum from n equals 1 to infinity of mu n of union from 1 to infinity of the EIs. This is equal to the sum from n equals 1 to infinity, and just looking at what each the fact that each mu n is a complex measure, we know that we can do this to it, that we can bring the union outside and make it a sum and keep the equality. And then here's where we use this Fubini's. This is basically an integral and integral. So we're flipping the order of these integrals with respect to the counting measure. So this is the sum from I equals 1 to infinity, sum from n equals 1 to infinity. And so just another note, remember what we needed to have happen in Fubini's theorem is you need to make sure that if you put the absolute value sign on the inside, then in taking the sum or integrating this thing is going to give you something finite. Like when you're trying to do Fubini's theorem on f of xy, then you got to make sure that this integral is finite, and then you can flip the integral signs when you are without the absolute values. And that is what we were doing here, because let's see here, what we have here is this is basically going to be, oh well, wait, now let's look at this. Yeah, because this mu has the the fact that this with absolute value is finite, that's exactly what we checked here. And so that's why we were doing this. I guess I didn't present that very well, but what we were doing is checking that the double sum with this absolute value sign in here does indeed converge. And it does. So because of that, we can switch the order of integration, and we get the mu n EI stays here. But now this is something that we know how to work with, because we know that the sum of the mu n's is mu of EI. Oh, well, it's not so much something that we know how to work with. It's something that we wanted in the first place, because now the statement is literally mu of measure of the union equals sum of the measures. And that's what we wanted. And that's the last thing we need to check. So hence, mu is a measure. So then, let's see here. So I'm trying to think if there, yeah, we did need to check that this is a measure, and now we need to check that basically this. Now I claim that the limit as n goes to infinity, the sum from 1 to n of mu j is equal to mu. And this should be obvious. This holds because I'm doing this off the fly, so it might be a little sketchy, just because I didn't feel like writing this out, because this is kind of the less important part of the proof. But anyways, so this limit, this whole limit definition here, this is all has to be in terms of the norm that we have on mx. And so what we're looking at is the difference between these two measures. I'm going to flip it around. So mu minus the sum from 1 to n of mu j, because what is this equal to? This is just the sum from n plus 1 to infinity of mu j, and this is less than or equal to the sum from n equals, not n plus 1. Oh, yeah, the sum from n plus 1. I'm not putting in the index. I'm not putting in the j equals n plus 1. I'm just using a shortcut. So that's less than or equal to this. And this goes to 0 as n goes to infinity, since the series converges absolutely. Now that I'm looking at this, there's nothing really special about this particular case I used here. So I think that stating this, that the limit of this is this in norm, is kind of, you get it for free with the theorem. All you really need to check is that what this limit is, this thing here is actually an element of the space you started with. So, and that's probably why I didn't write it down, because it's not really relevant here. So anyways, so hence every, just going to write absolutely convergent series to save space because I'm running out of it in mx converges. Hence mx is complete and thus Banach, because it's a complete space that has a norm on it. Alright, there we go. This completes the proof.